Okay, so welcome back, and now we're going to look at other techniques of evaluating limits. Okay, so before we found that we can find the limit of functions, even rational functions, by just evaluating the polynomials at a, right, at the limit, where the limit is tending towards. But remember, that's not always the case, right? And also remember that especially with rational functions, as we've seen before, they're not always defined at the limit. Okay? So how do we handle those? Because we can't just plug in a because it's undefined. But as we know, that there are plenty of examples of functions that we take the limit of where the limit does exist, even though the function is undefined at that value. Okay? Now, how do we handle those? There are different techniques to handle those. So let me show you. So what we're going to do is we're going to use the fact that we know that if it is possible that we can have something like this. For example, oops. Oops. Okay, so this is certainly true, right? So if for all x not equal to a, we have f of x is equal to g of x over an open interval containing a, then the limit as x approaches a of f of x is equal to the limit of x as x approaches a of g of x. Now this is certainly true. Okay, so let's do an example. Okay, so let's look at the limit as x approaches 1 of this function okay. Now, if we evaluate this at 1, what do we get? We get 0 over 0, which is undefined. Okay? But if we notice, we have a difference of two squares here, and we can write this as the limit as x approaches 1 of x minus 1 times x plus 1 over x, oops, x minus 1. Now notice that these are the same. Okay? And so we can factor out the 2. Right? So then this would equal the limit as x approaches 1 of x plus 1. So what is this saying? This is saying that this and this behave exactly the same as long as x is not equal to 1, because we just removed that. Okay? So the difference is, if we look at the graphs of these two functions, and I'm just going to sketch the graph of these two functions, they're exactly the same. Right, so this would be, let's call this f of x, and we'll call this g of x. So this would be f of x, okay? This would be the graph of g of x. Now the only difference is guess what? Is at 1, we have a hole in the graph. So notice that both of these graphs are exactly the same, behave exactly the same, except at x equals 1. That's where the discontinuity comes in. And so what we did here by factoring and canceling is we removed that discontinuity, and now what we could do is to this one, because now there's no discontinuity, is we can say that this is equal to what? Well, as x approaches 1, it's going to be 1 plus 1 equals 2. So we know the limit of the original expression is 2, using this factoring and canceling technique. Okay? Because again, just because there's a hole in there, the hole makes this an undefined, right? Because we get 0, 0, which is an indeterminate form. So we get 0 over 0, which doesn't tell us anything, other than the fact that there's something going on. Okay? But here, we can remove that discontinuity by factoring and canceling, and now we can find the limit like we did before. Okay? That's it. Have a great day.